Okay, so the next thing that we have here is some exercises related to the distance formula and locating some points in the three-dimensional space and so on and so forth. So the first exercise that we have is you want to find the distance between, for example, these 2 points, 2, 3, 5, 2, 3, 5 and 4, 3, 1 and 4, 3, 1. So we said that basically if you have 2 points P with coordinates x1, y1, z1, and you have the point Q, for example, with coordinates x2, y2, and z2, then PQ is equal to the square root of x2 minus x1 whole squared plus y2 minus y1 whole squared plus z2 minus z1 whole squared, and so based on this formula, the distance between these two lines, these 2 points, if I call them P and Q, that would be PQ is equal to the square root of 4 minus 2 whole squared plus 3 minus 3 minus 3 whole squared plus 1 minus 5 whole squared. And that is basically 2 squared, which is equal to 4. 0 squared is 0. Is 0 squared is 0, and negative 4 squared is basically negative 4 squared. That is equal to the square root of 4 plus 16, which is equal to the square root of 20, and that is the square root of 4 times 5, which is equal to 2 square root of 5. So question number 1, the first part is, and that is 12.2, 2 square root of 5. Part 2 of this question is the points are negative 3, 7, 2, and 2, 4, 1, negative 1. So here what you need to do is, again, PQ is equal to the square root of x2 minus x1, 2 plus 3 whole squared, plus 4 minus 7 whole squared, plus negative 1, negative 2 whole squared, which is equal to 5 squared, negative 3 whole squared, negative 3 whole squared, which is equal to 25 plus 9 plus 9, that's 18, plus 25 is equal to 43. The square root of 43. Now the square root of 43 is, I think 3 is a prime number. I think 43 is a prime number, is a proven prime. So the square root of 43 cannot simplify it any further. Part 2 of this question is square root of 43. Part 3, you have basically negative 1, 3, negative 4, and 1, negative 3, and 4. So then again, PQ is equal to the square root of 1 minus 1 is equal to 0, negative 3 minus 3 is equal to negative 3 minus 3 whole squared plus negative 4 plus 4 plus 4 whole squared which is equal to the square root of negative 6 squared plus 8 squared, which is the square root of 36 plus 64, which is equal to the square root of 100, which is equal to 10. So part 3 of this question is 4.2 part 3, negative 1, 3, negative 4, 1, negative 3 and 4. Oh, there is something wrong here, I suppose. Okay, so let's say that you have the square root of 1 plus 1 squared plus negative 3 minus 3 squared plus 4 squared which is equal to the square root of 2 squared plus negative 6 squared plus 8 squared, which is equal to the square root of 4 plus 36 plus 64, and that is the square root of 90, 100, 104. 104. Now 104 is 2 times 52. 2 times 52, and 104 is 2 times 52, and 52 is not divisible by anything really. No, I'm sorry, 52 is of course divisible by 2, which is 22 times 26, 2 times 13. So you have 2 square root of 26. 2 square root of 26. So that was part 3 of this question. Part 4 is basically the points are 2, negative 1, 3, negative 1, 3, and negative 2, negative 2, 1 and 3. So again, PQ is equal to negative 2 minus 2 whole squared plus 1 whole squared plus 3 minus 3 whole squared, and that is equal to the square root of negative 4 squared plus 2 squared plus 0 squared, which is equal to the square root of 16 plus 4 square root of 20, 2 times square root of 5. And that is part 4 of this question. Now question number 2. Question number 2, you want to show that these 3 points are collinear. So you have negative 2, 3, 5. You have 1, 2, 3. And you have 7, 0, negative 1. If I call these points, for example, A, B, and C, if I draw a coordinate system, and if I set this as my y-axis, set this as the as the z-axis, set this as the x-axis, for example, and over here I have -2, 1, and 2, and draw a line parallel to the y-axis, and 3 units along the y-axis would be 1, 2, and 3. A line parallel to the x-axis would be this line over here. So this point is basically the point. So this point over here is then the point -2, 3, -2, 3 in the xy plane. So then you can drop a perpendicular to the xy plane, and on this line, basically pick 5 units here, 1, 2, 3, 4, and 5. That is your point, which is A, -2, 3, and 5. So that is that. That is that. I have another point, 1, 2, 3. So 1 would be this thing over here, this point over here, parallel to the y-axis, 2 units across the y-axis, parallel to the x-axis, this point over here, go up 3 units, 1, 2, and 3, and this point is B. And this point is B. And the third one, you have 7 units across the along the x-axis. So you have 1, 2, 3, 4, 5, 6, and 7. 0 units across the y-axis and -1 units across the -1 units along the z-axis, and this point would be C. Now if I draw a line through these points, you can see that they seem to be collinear. There's a point over here that goes through the line, this point that goes through the line, and this point C that also goes through the line. This is the x-axis. So what you need to do, now if these 3 points are collinear, AB plus BC is equal to AC. So what that means is that, now if I calculate, for example, AB would be equal to the square root of 1 plus 2 whole squared plus 2 minus 3 whole squared plus 3 minus 5 whole squared, and that is equal to the square root of 3 squared plus -1 squared plus -2 squared, and that is equal to the square root of 9 plus 1 plus 4, and 9 plus 1 is equal to 14. That's the square root of 14. So AB is equal to the square root of 14. Next, BC, these 2 points, is the distance between them is the square root of 7 minus 1 whole squared plus -2 whole squared plus -1 minus 3 whole squared, which is equal to 6 squared, -2 squared, -4 squared, which is equal to the square root of 36 plus 4 plus 16, which is the square root of 56. Now 56 is 2 times 28, 2 times 14, 2 times 7, which is 2 times the square root of 14, which is 2 times the square root of 14. So that means that BC is equal to 2 times the square root of 14. Now AC over here, AC is equal to the square root of 7 plus 2 whole squared plus negative 3 whole squared, negative 1 minus 5 whole squared, which is equal to 9 squared plus negative 3 squared plus negative 6 squared, the square root of 18 plus 9 plus 36. 45 plus 18 is equal to 13,163. The square root of 63. Divide by 3, you will get 21, I suppose. 21 times 3 is equal to 363. And then that's so 63 is equal to 21 times 3, and this is 3 times 7. This is 3 times 7, so that's 3 times 7 times 3. That's 63. So that's 3 square root of 7. That is 3 square root of 7. Let me check here. 7 plus 2 whole squared, negative 3 whole squared, and negative 6 whole squared. 9 squared is equal to 81, I'm sorry. 9 squared is equal to 81. Is equal to the square root of 81 plus 9 plus 36, which is equal to 45. 81 plus 45 is equal to 6. Mm. 126, and that is 2 times 63, and that is 2 times 3 times 21, and that is 3 times 7. So that's 3 times the square root of 14. So that means that then 126 is equal to 3 squared times 14. So the square root of 126 is equal to 3 square root of 14. 3 square root of 14. Now if I write AC over here, 3 times square root of 14. Now you can come over here and check this equation, and so you see AB is equal to square root of 14, BC is 2 times square root of 14, and AC is 3 times square root of 14. 3 times square root of 14 is equal to 3 times square root of 14. That is true, which means that A, B, and C are collinear. Okay, so the next question that we have is we want to verify that, for example, These 3 points are the vertices of an isosceles triangle. So you have the point 0, 7, negative 10. You have the point 1, 6, negative 6. 1, 6, negative 6. And you have the point 4, 9, negative 6. 4, 9, negative 6. We call this A, call this B, and call this C. So, if that is the case, then, for example, you see this is on the YZ axis. This is on the YZ axis, this point over here. And your x coordinate is 0, meaning that if, let's suppose that, for example, this is the x-axis, and this is the y-axis, and this is the z-axis, then this point over here, you have no coordinate 0 intercept on the x-axis. That means that you're not moving along the x-axis, you're just moving along the YZ axis, this vertical plane, this YZ plane in space. So you go 7 units along the y-axis. So that's 1, 2, 3, 4, 5, 6, and 7, and then negative 10 units down. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and that would be your point 8. Then you have the point 1, 6, negative 6. 1, 1, 2, 3, 4, 5, 6. 6, negative 6. 1, 2, 3, 4, 5, and 6. That's point B. And then you have 4, 9. 1, 2, 3, 4, 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. 4, 9, negative 6. We have 1, 2, 3, 4, 5, and 6, which makes no sense. I don't know, maybe probably this way, for example, this is an isosceles triangle, if it's possible. Meaning that if this is point C, then AC is equal to AB, probably. So now I'm going to test AC and AB over here. If AC is equal to AB, so if AC is equal to AB, then triangle ABC is isosceles. Isosceles is isosceles. So now AB is equal to the square root of 1 squared plus 6 minus 7 is equal to negative 1 squared. Negative 6 plus 10 is equal to 4 squared. And over here I have 1 plus 1 plus 16, which is equal to the square root of 19. 2 times 9, 19 is 18 is basically 2 times 8 is equal to 16. 18 divided by 2 is equal to 9. So 19 is, of course, is a prime number. 19 is a prime number, right? Is a proven prime. So the square root of 19 is AB. No, I made a mistake here. I'm supposed to take AC and BC. I'm sorry. AC and BC. AC and BC. Okay. AC and BC. AC and BC. So then AC is equal to the square root of these 2 points. So 4 squared plus 2 squared plus 4 squared, which is equal to the square root of 16 plus 4 plus 16, 32. 32 plus 4 is equal to 36 is equal to 6. And BC is equal to 3 squared plus 3 squared, which is equal to 36 plus 36 equal to But of course there is one more possibility. You see over here the x-coordinate of this point is 4. The x-coordinate of this point is 1. And the x-coordinate of this point is 0. So the mistake that I made right now, and this is definitely of course not the square root of 3 squared plus 3 squared is equal to the square root of 3 squared plus 3 squared is equal to basically 9 plus 9, which is equal to the square root of 19. Now if you remember, when I calculated, so this is AC and this is BC, when I calculated AB, that was equal to basically 1 squared plus again negative 1 squared. 6 minus 7 is equal to negative 1 squared plus 4 squared, which is equal to basically 1, the square root of 1 plus 1 plus 16, which is equal to the square root of 18. Now you see that AC is equal to BC actually. AC is equal to BC. Now over here from this diagram, if you look at this diagram in a 2D way, I mean, if you think of this as these lines being on a two-dimensional plane, of course these two lines, and that's the mistake that I made right now, which is a pretty bad mistake, because you need to train your brain to read these distances now in terms of basically 3D distances, not 2D distances. So what that means is that you see this point over here, the y-coordinate of this point, is around 1, 2, 3, 4, 5, 6. The y-coordinate of this point is around 7, the same y-coordinate more or less. And their z-coordinates are, well, the z-coordinate of this point is 2, 4, 6. The z-coordinate of this point is, over here you have negative 6, 6 and 10. There is not much difference there. But the x-coordinate of these points, for example these 2 points, this point over here point B and this point over here point C, the x-coordinate are basically 3 units apart. That means that BC, this distance over here, BC, is actually the same thing as AB, which is basically this distance over here. These two are actually equal distances, but if you think of this in three-dimensional space, And from this diagram, it's not very clear. So what you can do, you can use Geogebra. You can use Geogebra and write over here the points that you have basically. So the points are 0, 7, negative 10, for example. So you can write A as 0, 7, 0, 7, negative 10, and I think I need to refresh this thing. So if I write this point as A 0, 7, negative 10, and we'll do it on the other monitor, and then I'll come back over here. I don't know how to. Now, if you don't know how to, which I do not know right now really, if you do not know how the format of a point, for example, is in this calculator, you can go to the Tools tab and go and pick a point, and for example, put a point over here, somewhere over here. And now the point has been placed over here, and now I can bring it up, bring it down. I can do anything with the point. And it's a pretty amazing tool, of course. It's not perfect, still has bugs and everything, but still a very perfect tool. I mean, a very interesting tool and very useful tool. Now, you see this point over here. This is your X plane, this is your Y plane, and this is your Z plane. And I suppose now if you go over here, this is 2.43. This is 2.43. If I put the point across here, it's going to be this doesn't make any sense. Now I'm exactly on this axis, and you see that my Z coordinate is 0. So when you read the graph over here, it could actually mislead you. So now the graph is basically at your X coordinate is 3.16. So that means that the red axis is the green axis. Negative 5,8 is, if I go over here and move this thing, you can see that I am at negative 5,6 along this green axis. So that means that it's actually upside down. I need to move it. So now you can see that these numbers over here are negative. Now these numbers are positive. These numbers are negative. These numbers are positive. So I need to move this a little bit. It seems that it doesn't stop. Now you can see that all of these numbers are positive. All of these numbers are positive. And all of these numbers are negative. All of these numbers are positive. These numbers negative. These numbers positive. So Now the coordinates of this point in this coordinate system are the x coordinate 3.16. But over here I'm reading, which is right, because this is actually your x-axis, so your x coordinate is 3.16. Your y coordinate is negative 5 point something, negative 5.8, which makes sense. And your z coordinate is 0, because I did put the point exactly on the axis, or exactly on the plane. But of course, you need to be careful about this, because you might look at this thing from basically upside down, from the top. You might be looking at the point, and you might not actually see the height of the point. Right now the height of the point is 0, meaning that along the z-axis the height is 0. And as you can see, the point is exactly on the plane. So in that respect, it's not really, it doesn't show you at least this third dimension over here properly. So you need to be careful about that. Now if I go to, there was a calculator over here. There was this calculator over here. Return to three-dimensional coordinate system. And there is no tool over here to do that. Okay, so let me use this calculator. Let's see how this thing works. So if I go to over here to 3D Cartesian plane, and if I create a point, for example 2, 5, 10. It gives you either an equation or a function. So this is equation and function, data set, parametric inequalities, graph controls. So you cannot plot any points over here. I don't think you can plot any points in here. And this is just a demonstration. You cannot really plot anything in here. And the only other thing that I know is basically anyway, I guess our best choice right now, our best option right now is just this thing over here until we find something better. So anyway, the green axis, the red axis is your x-axis, the green axis is your y-axis, and the blue axis is your z-axis, and you have to be careful about the height of these points. And right now, for example, this point is exactly on the xy axis, for example, on the xy plane basically. So now I'm going to change the coordinates of this point to what we had over here, which is basically 0, 0, 7 and negative 10. which is some point which is supposed to be some point here, which is not there. 0, 7, negative 10. 0, 0, 7, negative 10. Okay, so the point is down here. We have to kind of zoom out to see the point. Now you can change these scales over here, I suppose, so that you don't have to zoom out so much. I think you can go over here and do show axis, show plane. Oh yeah, you can show the plane as well. Show grid, you can show some grid over here as well. And then you can, what is this projection? Perspective projection, projection for glasses, oblique projection, no. Snap to grid, zoom to fit. And you have some settings over here. And then you have the show axis, y-axis is vertical, no. You can change this. Colored axis, navigation bar for construction steps, miscellaneous background color. You can have some background color, which I don't want right now. You have some clipping, use clipping or show clipping, clipping box size, which is not important right now. Now you want it about the x-axis, you have the show axis, show numbers, positive direction, directed direction only, distance is label unit, selection allowed. Okay, it seems that you cannot actually do that. Okay, so now the point is over here, right? The point is down here. Now the problem is that I cannot really see. The problem is that I cannot really see whether I am whether I know I'm down here. So that means that, so basically I have the first octant, second, third, fourth, and down here I have the fifth octant and the sixth octant over here. So now, looking at this graph, there is no way for me to know whether I'm in the fifth octant or the sixth octant. So, but since both x and y are positive, that means that I am actually in the fifth octant. But it would be nice if I could see in which octant I was. So that's not possible to see here either. And that is all because of the way that this thing has been programmed. Now this point is over here, and as you can see, the second point that we had was 1,6 was 1,6, negative 6, which is basically this point over here. This is point B, and point C was 4, 9, negative 6. 4, 9, negative 6. So now I have these 3 points over here, and these are the exact graphics over here are not really great. Okay. So now, basically we saw that over here, we saw that AB was equal to BC. AB was equal to BC. So as you can see, AB and BC, when I look at these points from a two-dimensional perspective, they don't seem to be the same distances. But if I go down here, you see over here, from this perspective, for example, AB is actually equal to BC. I mean, even if you eyeball it, you'll see that AB is equal to BC. But the problem here is that you have no, basically, suppose that over here, so in this coordinate system, what I have is basically these planes over here, and I can, with respect to these planes, I can see things more clearly. I know basically where things are with respect to these planes. But the planes are not simply there in this. Over here, the planes are just not there. So I don't really know where these points really are, because when I look, I have to, I mean, there is no other way to see really. I mean, when you look and when you want to recognize dimension has to be with respect to something. For example, some background or some other object or something like that. Otherwise, dimension doesn't mean anything. So that's the problem here. But, well, again, I will find some better tool than this. But for now, we can just work with this until we have some better tool to use. So then basically, now whatever the case, now we showed that basically AB is equal to AC, AB is equal to BC, and so the triangle ABC is an isosceles triangle. But you need to be, again, you need to be careful with these points, and they can very easily mislead you, basically, based on, because here you're looking at things in three-dimensional space, and your mind is accustomed to, at least when it comes to coordinate systems or rectangular coordinate systems, your mind is accustomed to 2D dimensional, to a 2D dimensional system. So you might not be aware of the fact that your mind is looking at this thing from a two-dimensional point of view, and then you might be seeing things the way that they are actually not. So you need to be careful about that. So there is a couple more questions over here. We will do them as well, and then we'll move on to the next things over here. Okay, so now we have 3 points over here, and the points are 0, 7, 10, 0, 7, 10, and -1, 6, 6, and -4, 9, 6, and -4, 9, and 6. Let's call this A, let's call this B, and let's call this C. And you want to show that these points are the vertices of a right angle triangle. Vertices of a right angled or a right triangle. Now you know that if, for example, suppose that in a right triangle, if you have your right angle over here, and this is, for example, ABC, then AC squared as a distance between point A and C. So AC is the distance between the point A and C, and BC is the distance between point B and C, and AB is the distance between point A and B. So then AC squared is equal to BC squared plus AB squared. If this relationship exists between the side lengths of the triangle, you can conclude that if that is the case, then triangle ABC is a right triangle. And in geometry, there is basically always theorems are basically in this form. There is an if, there is an then, there is a then. And sometimes the converse of a theorem is also true, meaning that, for example, sometimes, depending on the situation, you can say that, for example, if triangle ABC is a right triangle, then we need to pay attention to the words if and then. Then, basically, then this relationship exists between the side lengths of the triangle, meaning that then you can write AC squared, for example, is equal to AB squared plus BC squared. Now, as you can see, this is the exact opposite of what we said over here. So this is called, technically this is called the converse of this statement. If you think of this as a statement, so then you can call this a statement P, you can call this a statement Q. So, and then you can of course break this down into two statements, meaning that you have, for example, some if over here and some statement over here, and then you have some comma, you have some then over here, and another statement over here. So I can call this a statement P, and I can call this a statement Q, and then write if P then Q, which can be written in mathematical notation. You can say if P then Q. That's basically that. Now the converse of this would be if Q then P. If Q then P, and it will the notation for that is if Q then P. And since basically you have basically you have if P then Q, and if Q then P, meaning that this statement is true, and the converse of the same statement is also true, then instead of writing this whole thing in basically this takes up a lot of space, and it's not a very it does use a lot of words to explain this situation. So then in order to explain this situation in fewer words, then you can say that P, if and only if Q. That means that, and the notation for this is basically this notation. You write this as P if and only if Q. You need to pay attention to basically that this is a double-headed arrow. This is read as P if and only if Q. That means that what this means is that P then Q and Q then P and Q then P. So what that means is that, now why I said all of these things is that in geometry things are always like this. For example, one theorem in geometry which is related to the Pythagorean theorem is that if this relationship exists between the side lengths of a triangle, then the triangle is a right triangle. And if a triangle is a right triangle, then the same relationship exists between the side lengths of the triangle. So you need to be careful about this. You need to be careful about this and about the fact that, for example, when you say, suppose that, for example, you say that, for example, in the same situation, if AC squared is equal to AB squared plus BC squared, then triangle ABC is a right triangle. Okay, so suppose that you say this. Now this does not necessarily mean that then if you have a right triangle, then this must be the relationship between the sides. The only thing that this means is that if this relationship exists between the side lengths of the triangle, then the triangle is a right triangle. That's the only thing that it means. You're not supposed to basically make sense of this statement. You are not supposed to make sense of this statement in any other way than the way that this statement has been written. This is the only thing that it means. Usually in day-to-day life, in our day-to-day lives, what we do is that, for example, if somebody says that, for example, she is a good person, or let's say instead of she, to make it unambiguous, for example, if somebody says that Susan is a good person, what this means, depending on the definition of good, for example, supposing that good has a definite definition, which it doesn't, of course, in our day-to-day lives, good doesn't really have any definite definition. It's a subjective concept. It's not objective, really. I mean, good has as many definitions as there are people on planet Earth, really. So there is no real definition for this word. But I'm assuming that this word good has a definite definition, has an objective definition. Now, if in our day-to-day lives, when somebody says that Susan is a good person, people automatically assume that Susan is not a bad person, which is not necessarily true. Which is not necessarily true in the mathematical sense and in logical sense. It's not necessarily true that when somebody says Susan is a good person, that it means that Susan is not a bad person. That doesn't really apply to mathematics. So you need to be careful about the conclusions that your mind makes in such situations, and you need to be careful about that. Now back to our problem. The points that we had here were basically these, and in order to make sense of this situation, you need to know where the points actually are. So in order to do that, I'm going to just plot these points in a coordinate system and see if we can actually see the points in a normal coordinate system, in a 3D coordinate system drawn on a 2D plane, which is what I'm using over here. My screen is just a 2D plane, but then we are trying to use it as a 3D plane, really. So then I can basically have a y-axis over here. I can have the z-axis over here, and I can have the x-axis over here. And so 0 would be 0 along the x-axis, 7 along the y-axis, 1, 2, 3, 4, 5, 6, and 7. And perpendicular to this plane, 10 units up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this would be point A. And you can see that this point is exactly on the YZ plane. It is exactly on the YZ plane. That the x coordinate of this point is 0. Now I have another point over here, which is -1, 6, and +6. So -1 over here. Draw a line over here. 1, 2, 3, 4, 5, 6, and some point, some line like this, and then this point is basically -1, 6, and then perpendicular to that, some point over here, and then 6 units up would be 1, 2, 3, 4, 5, and 6, and that is your point B. That is your point B. I'm going to erase all of these things because I don't want to make this unnecessarily crowded. Oh, that was the x-axis, I'm sorry. That was the x-axis. This is x prime. This is x prime. And then the third point is -4, which is 1, 2, 3, and 4. Parallel to the y-axis, 9. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. And so then this point would be the point of intersection of the two points, and then perpendicular to that, 6 units, 1, 2, 3, 4, 5, and 6. This point over here is basically this point C. Now you see that this point is way behind these 2 points, and this point is basically at basically -1 and somewhere around 6, 7. This point is basic. So point B is actually behind point A, and so you need to think of that in that way. But still, I cannot really understand. I cannot really understand, or I cannot really see it in my mind that if I, for example, connected these points together, I don't really know if this going to be. I'm just looking at this thing from this viewpoint, and I don't really know what it's going to look like if I go for example back here behind the YZ plane, and if I look at the triangle from back there. So that is our problem right now, but I can assume that, pretty safely assume that, for example, this must be a 90-degree angle, probably. Now, again, the best tool that we have right now is basically this. Let me delete these points. Alright, this is 0, 7, 10. So 1, 6, -1, 6, 6, and negative 4 comma 9 comma 6, and now these are the points that I have, and you see you need to pay attention to this. This is, as we said, the red axis is your x-axis, the green axis is your y-axis, and the blue axis is your z-axis. And this is now the positive numbers. These are now the positive numbers, and these are the negative numbers. So, and the points are now seem to be in the right octet. So now if I go over here and take a look at these points from here, I can see that probably I can see a triangle in this plane. You see from here I can, all the 3 points are along the same plane, which is then from this viewpoint it's not going to be a triangle. But otherwise from here, for example, they are going to be triangle. So if I move this around, I'm going to see a triangle over here. So what that means really is that if I take a look at these, you see from this angle, from this viewpoint, the 3 points are basically, they seem to form a right triangle. And then if I go over here, remove this a little bit, you see from here the points are exactly on the same plane. And so I'm going to what I'm going to do, I'm going to take B as the vertex containing the right angle, and right AC squared is equal to AC squared, and then let me take a look at this thing from the other angle. Let me see what I see over there. I see. Okay, so there is still something interesting that you can see here. You can take a look at this thing over here, and you can see that of course this axis over here is supposed to be perpendicular to this axis. So that means that of course then it's not possible for me to show this axis exactly perpendicular to this axis the way that I have drawn these two axes. For example, the y-axis and the z-axis on this plane are clearly perpendicular, but the but the x-axis, for example, is not perpendicular to the y-axis. As you can see it over here, the angle is like 30-40 degrees or so, 45 degrees, the angle between the y-axis and the x-axis, and so is the angle between the x-axis and the z-axis. And you can see the point, you can see these points in this orientation, but you need to pay attention to the fact that your axes are actually in this orientation, meaning that now looking at this coordinate system, you can see that this is the y-axis and this is the x-axis, and this is the z-axis, this is the y-axis, and this is the x-axis. And well, in this orientation, for example, in this orientation, your y-axis is basically, well, still over here, the axes are not perpendicular, so it's not really possible to show that. But the points are more or less in the same orientation, meaning that you get your point A, point B, and point C over here. But the problem is that point C right now is up here, but over here the point C is down here, meaning that I'm seeing the point C over here as having kind of the same elevation as point B, but point C over here is up here. Let me take a look at the okay, there's something that I need to look up really. Well, okay. Well, I was kind of assuming that what I did over here was not really right, because you see the elevation of this point is a little bit different compared to, for example, what I've drawn over here. But it's not wrong, and I suppose we can basically take this as a base system and work based off of this system over here, and then of course find a better system than GeoGebra. But in the meantime, we can use GeoGebra in order to clear any doubts we might have. So this system is a little bit tricky until you get the hang of it, really. So what I'm going to do now is, I suppose, now let's really see if angle B is the right angle, or if angle A is the right angle in this system. It seems that angle B is the right angle, but let's see. We will do the rest of this in the next video.